Hello everybody. So now we'll start talking about the diffusion coefficient or estimation of the diffusion coefficient in the liquid phase, and we will follow the same procedure that we followed in the gas phase. So we will discuss many equations or different equations, and for each equation we will talk about the parameters and the conditions under which I can use this kind of equation. But first we will start with the theoretical form of the equation, which is similar to the kinetic theory of gases. In the case of gases, here we have the Stokes-Einstein equation, which assumes similar assumptions of spherical particles and elastic collisions. So here what we have is the diffusion coefficient as a function or equals the Boltzmann constant multiplied by the temperature divided by 6 pi RA. RA is the solute particle radius, and mu b is the solvent viscosity. The equation can be rewritten in the form of d multiplied by mu b and t divided by t equals the Boltzmann constant multiplied by a function of the molecular volume. It's written in this form because this is a form that is common to C, which is the left hand side. The d multiplied by mu divided by t is a commonly used form of the equation, so we would keep it like this because it's used a lot this way. Before we leave this equation and go ahead and see the actual equations that we use, we need to take a look at the equation and notice some points. The first point is that the diffusivity is directly proportional to temperature, so it's not 1.5 as it was in gas phase. There is no dependence on pressure here, which is a good point to notice, and there is and it's inversely proportional to radius, which is similar to what we have in the gas phase, and it's inversely proportional to the viscosity of the solvent. So here is the first time to notice the viscosity in the equations that we are using to calculate the diffusion coefficient. In the gas phase it was never discussed because viscosity of gases is very low, so it's not effective. But in case of liquids, it makes a lot of sense to have the diffusion coefficient inversely proportional to viscosity. So imagine if you have let's say sugar that you have or want to diffuse in water and diffuse in honey. So of course in honey it's gonna be more difficult and it's gonna create more resistance to diffusion, so the diffusion coefficient would be much lower. One other point that I want to draw the attention to is the distinction here between the solvent and the solute. So here we cannot replace A and B. So in the gas phase we said that if you flip A and B, it's not going to make any difference. The diffusivity of A and B equals the diffusivity in B and A. This is not the case here. You will have RA, which is the solute particle radius, and mu B is the solvent viscosity. So you have to make sure that you know which is which. In the gas phase it was easy. You just take the data of the two species and it's done. Here it's not this way. So from the diffusion coefficient form that we have from Stokes-Einstein equation doesn't create or produce good results, and there is a very high margin of error in using this equation. That's why we use the empirical correlations that are produced based on the experimental data. And as we said before, in the gas phase we have polar gases and nonpolar gases, or polar molecules and nonpolar molecules. Here we will have something similar, which is the electrolytes and non-electrolytes. Electrolytes are the liquids that produce ions, like acids, like bases, like salts, or salt solutions. If you have like salt in water, it will conduct electricity, and that's why we can consider this as an electrolyte. So the main categories of the electrolytes are acids, bases, and solid and salt solutions, which conduct electricity by the transfer of ions, not the transfer of charges. So in non-electrolytes, so non-electrolytes would be the corresponding to the nonpolar in case of gases. So this would be the simple case where we have simple equations. It's the left-hand side is exactly like the Stokes-Einstein equation. Here we have the equation is a function of only 3 parameters besides the mu and t. These are the phi b, which is the association parameter. Association parameter is a parameter that takes into account the association or the kind of bonds that take place between the molecules. So if the molecules are associated, so it means that they kind of agglomerate or something like this. So they act like bigger molecules, and that's why we have here phi b. And this m is the molecular weight of the solvent. So these two are related to solvent, and Va is the molecular volume of solute at its normal boiling point. What we can notice here is that the parameters that we need to calculate the diffusion coefficient are viscosity. Of course, we should know the temperature, so it's the viscosity, the phi b, mu b, and Va. So the only parameter that is related to the solute is the molecular volume. The rest of the parameters here are for the solute. For the solvent, I'm sorry. So mu is the viscosity. It should be easy to find from any textbook of properties of materials or liquids. Mb is the molecular weight, so it's gonna be only the point of knowing how to calculate or get the values of phi b and Va. So for Va, it is available in tabulated data for some molecules. So I have hydrogen, oxygen, nitrogen, carbon dioxide, carbon monoxide, nitric oxide, and like a list of a good number of molecules. And you'll notice that most of them are gases, and this doesn't make any contradiction with using the equation in the gas phase, in the liquid phase, because we can have gases that diffuse in liquids. So for instance, we know that oxygen dissolves in water, and that's why fish can survive underwater. And this is something that happens a lot. So you can dissolve gases in water or in liquids in general, and get this gas to diffuse from high concentration point to the lower concentration point. So maybe you can have a compound that is not listed here in this table. So if this is the case, so you can estimate the molecular volume using the atomic volume of the elements that form this molecule. So let's say you have bromine, carbon, chlorine, hydrogen, iodine, nitrogen, oxygen, and sulfur. So we have the atomic volumes of all these elements. And here you would see that you will calculate the atomic or the molecular volume by the summation of atomic volumes. So if I have methane, so it's going to be 14.8 plus 4 multiplied by 3.7. So these are numbers that I can use. There is one correction factor that I must take into account, which is used in case of having a molecular structure that has cyclic or contains rings. So something like 3-membered rings, which have three bonds in this ring. There are 4 bonds in the ring, 5 or whatever. So for these cyclic structures, they have smaller volumes than the straight structures. So for this cyclic structure, we will deduct these numbers. So if you have, for instance, 4-membered rings for this molecule, for instance, I will calculate the summation of the molecular or the atomic volume. So it's going to be 4 multiplied by the volume of 1 carbon atom, and 8 multiplied by the molecule or the volume of hydrogen atom, and then subtract 8.5 because of this square structure or the 4-membered ring. For benzene, naphthalene, and anthracene, we will have these deductions as well. I have 15, 30, and 47.5. So this is just correction factors to take into account the reduction in volume due to the cyclic structure. In case I don't have either, even after checking this table, I have a molecule that contains some of the elements that are not here, I can use this relation to calculate the atomic or the molecular volume using the critical volume of this compound. So this is the last option in case I don't have the possibility, or it's not possible to use the previous relations and the table to calculate the molecular volume. So now the last parameter to calculate or find is the association parameter, which is phi b. We know the phi b for water, it's 2.6, for methanol is 1.9, ethanol 1.5, and for any nonpolar solvent it's 1. So this is all the information that we know about the association parameter right now. So finally, this note, I want to emphasize on this note that the equations distinguish between the solvent and the solute, and the diffusivity of A in B is not equal to the diffusivity in B in A for liquid phases. So let's try to solve this equation or this problem. I want to estimate the liquid diffusion coefficient of ethanol in dilute solution of water at 10 degrees Celsius. So the equation is, as you notice, it's very simple and straightforward. You just substitute directly in this equation. The information that we know are the temperature, it's 10 degrees Celsius, which is going to be to 83 degrees Kelvin. Viscosity of water, I can get it from any textbook, or even you can check online, you'll find a lot of values. So the point here is to calculate VA and phi B. If we check the table, we will find that phi B equals 2.6 for water, so it's not a big deal. But now we need to, I think I have something wrong here, it's 2.6, not 2.26. So we know it for water is 2.6, the viscosity is 1.45 centipoise, and this is something to notice, that the viscosity is in centipoise. And here we calculate the molecular volume of ethanol, which is 2 multiplied by volume of carbon plus 6 multiplied by volume of hydrogen plus 1 multiplied by the volume of oxygen, which is 59.2. So now we have all the parameters. By direct substitution, we will find that this diffusion coefficient is going to be 8.5 multiplied by 10 power minus 6 centimeters square per second, or multiplied by 10 power minus 10 if it's meters square per second. This agrees with the ranges that we mentioned before we start the calculations of the diffusion coefficient. We mentioned that for liquid phase, it's gonna be from 10 to the minus 6 till to 10 to the minus 10. So this is falling within the range. So this is a good thing to check, or to be like something to check about the values that you calculate. The next video we will talk about other equations that we can use to calculate the diffusion coefficient. So I'll see you then.